Bom dia a todos. Hoje temos outra sessão do nosso colóquio de Programa de Pós-Graduação em Engenharia Física. Estamos felizes por ter recebido o nosso convidado, o Dr. Reza Amini. Ele é iraniano, fez doutorado em São Paulo, Universidade de São Paulo, na área de engenharia mecânica, trabalha muito com simulação de CFD, na área de fluidos, né? Ele tem pós-doutorado na mesma área, pela Universidade de São Paulo, no momento ele é um pesquisador na agência de ciência e tecnologia subterra no Japão. Então, eu vou introduzir também ele em inglês, eu vou dar o microfone, né, passar o microfone para ele começar a sua apresentação. Good morning to everyone. Today, we are happy to have Dr. Reza with us. He will give his presentation of his recent research results, and he's a doctor in mechanical engineering from University of São Paulo. He also has a postdoctorate degree from the University of São Paulo. Then he moved to Japan, and he's a researcher over there. He is working at the Japan Agency for Marine Earth Science and Technology since the last year. And he has a lot of experience to work with the simulations and CFD methods, like modeling of the computational fluid dynamics. He also has been working as an engineer in the industry in Iran. He also has experience like a professor at the university in Iran. And he shows a lot of interest to participate in our colloquium, since he's very interested to enlarge his collaboration circles with other peoples and friends. And we are happy to listen to him today. Dr. Reza, please put your presentation in the presentation mode, in the full screen mode, and you may start.
Okay, so everything's okay? You can see?
Right.
Okay, start?
Yes, sure.
Okay, so
thank you.
Thank you, Dr. Reza, Professor Reza, thank you very much, and hi, everybody. Before I begin my before I start my presentation today, I would like to say thank you for giving me this opportunity to make this speech here today. So my name is Reza Amini, and nowadays I'm a researcher scientist, industrial project in the Japan Agency for Marine Earth Science and Technology. And my experience and research line is about the computational fluid dynamics. And today I'm going to talk about some projects that this project started and funded with the University of São Paulo with Foundation for PESP. And until now, we are trying improving, and also we are publishing some papers about some part of the result. So today, I'm going to show you some part of the result, and I hope that be interesting. And I am ready for any cooperation with your department, and also any professors, any researcher wants to continue in this research line. I am completely ready to do this research or write any proposal or something. So start this presentation, and today I'm going to talk about fluidization. And before I start the presentation, I'm going to start with a simple introduction. Well, actually, fluidization is really important in the industry application because widely applied in the energy or chemical industry. And in the fluidization, here you can see the schematic drawing of a fluidized bed reactors, and inside we have a granular particles, and inside the fluidization we have upward blowing gas, and this gas can easily pass between the particles, so the particles can convert from the static-like state to the dynamic fluid-like state. So this process is called fluidization, and is very important for industry because is really important also for the oil company. So today, after this one, I try to bring some most important application of the fluidization. And here, like for example, extensive use of fluidization started in petroleum industry as fluid catalytic cracking, and in this industry, like solid gas reaction or coal gasification, and also we have different application about the fluidization. And if I want to bring one example, the most part, for example, 3/4 of all polyolefin are made by the fluidized bed process. So this is some of the most important application of the fluidization. And fluidization, like other process like sorry, can you hear me?
Yes, Reza, you can continue.
Yes, okay. If there is any problem or something, please tell me or something. Okay. So
Right.
fluidized bed, like other process like liquefaction or other parameters, we have some advantages or disadvantages. And here I try to bring some advantages like easily handling of the particles, because as I mentioned before in the last slides, due to the high gas velocity, we have movement of the particle inside the riser. So for this great mixing, we have like easily handling of the particle or easily transfer of the particles. So also due to the great mixing, we have a uniform temperature, uniform conditions, and also we have high like heat and mass transfer rates. And also this process, we have some disadvantages like complex hydrodynamics, and also calculation of the fluidization due to the non-linear behavior of the bed is really difficult because it's a really complex phenomenon. So if you want to investigate, it's really difficult. And also in the reactors, we have particles, and also due to the high gas velocity, we have movement of the particles. So for this reason, we have the high erosion inside the reactor. So we have some advantages and some disadvantages. And if I want to continue with these disadvantages, for example, this is one like the picture, and here you can see for every my slide, you can see the reference here. For these pictures, this is the reactors, fluidized reactors. As you can see, maybe the high reach until the 90 meters and the like 9 meters on the 3 meters. Doing experimental work, we need some like this space, or like physical experimental are too expensive because we have different particles, and also measurements like measurements are really difficult and also expensive. So based on this scenario, we try to select the alternative tools like computational fluid dynamics or like a CFD. And so here, this is the main reason why I selected the computational fluid dynamics. So based on the fluidization, now before go and start solving the problem, I'm going to speak a little about the fluidization regimes. Well, actually, this is a schematic drawing of the riser, and from the left-hand side to right-hand side, we have increased gas velocity. In the first picture, as I mentioned that in the process we have upward blowing gas, And this gas, in the first pictures, when the gas is not large enough, means the velocity is not large enough to act the whole weight of the particles, maybe we can see a small vibration inside the particles, so the height didn't change, so it's called fixed bed. And after that, with increase of the gas velocity, this gas velocity can support the laser, okay, so I can support the whole weight of the particles, so we can reach the point is called minimum fluidization, and as you can see here, the height a little increase. And after this point, with increase of the gas velocity, from the left hand side to the right hand side, we have different regimes until the end, like pneumatic part or regimes. So we have different kind of the regimes, and for my simulation, we need to select different gas velocity to support the whole like the regimes. And as I mentioned in the last slide, I selected computational fluid dynamics, and here the answer is here there is another question that with this computational fluid dynamics, can we solve the problem about the fluidization process or not? Here you can see the schematic drawing of the fluidized bed reactors, and this is the real fluidized bed. And simulation for the gas solid fluid real riser, due to the huge number of the particles, and we need to apply the larger scale simulation. Due to the larger scale simulation, we have very coarse grid size here. You can see, for example, here I applied the larger scale simulation, and after application, I can see here very coarse numerical grids. Inside the riser, due to the high gas velocity, the distribution of these particles over cross area in non-uniform fashion, and also this flow, like gas solid flow, inherently unsteady with large fluctuations. So for this reason, we can there is different streamers and clusters with different size inside the usually dilute regimes. And here for my research, and today I'm going to speak about the clusters and streamers with the size of the 10 until the 100 particles. It's called mesoscale structure. And we know that this mesoscale structure has effect on the flow behavior and with these coarse grids, we can't calculate the effect of the mesoscale structure in this riser. So what's the solution? For our case, we applied this, we want to transfer, or we want to switch from these very coarse numerical grids to a very small grid size. We can reach the finest grid size. So for this reason, I applied a subgrid model inside the very coarse numerical grid. So as you can see here, this is for example, one of my grid size. I applied the subgrid model inside this coarse grid, so I can reach the finest grid size. So now you can see that with this small grid size, I can calculate the effect of the mesoscale structure in the real riser. So, and if I want to explain by more details, as I mentioned before, this is the real scale fluidized bed. And after that, for example, I applied the larger scale simulation. With this larger scale simulation here. This is, for example, the riser. This is the real scale. And with this larger scale simulation, I can see the very coarse grids. So if I want to calculate the effect of the mesoscale structure here, I need to apply the subgrid model. So with this subgrid model, I can reach the finest grid size inside the very coarse numerical grids. And also for this subgrid models, I need to use some closures to recover the effect of the subgrid models. So after that, now there is another question that if I apply the subgrid models, my problem will be solved or not, because you imagine that this is the real scales. So if I want to apply this subgrid inside each grid. So in this case, I have huge number of the grid size, so the solving is really impossible because due to the computational source like computer or something, really we can't because it takes too much time. So what's the solution? Another solution is that I need to apply another approach to decrease the computational time. So in the next slide, I will explain that how I want to save the time in my simulation. So for my simulation, I applied the two fluid model. Here you can see different, and my two fluid model, I have two different phase, gas and solid, and both phases treated as interpenetrating continuum phases. And also I need to use some microscopic closure. So for this reason, two fluid model is called microscopic two fluid model. And these closures, for example, for the solid phase stresses, I applied this old theory is called kinetic theory of granular flow for the solid phase stresses, and also for the interaction between the phases, I applied the Venn and U model. So, and the more details about the equations you can find in our recently paper. So I applied two fluid formulation inside the highly resolved simulation. Well, actually, as you remember, this is my periodic domain. This is the large scale domain. I applied the subgrid model inside, so I can reach the finest grid size. Is called highly resolved simulation. So as I mentioned before, you imagine that in the real scale, I want to apply all these small grid size. Well, really solving impossible due to the computational source. Really, we can't solve this simulation. So this is inside the each grid size. As I mentioned before, I applied two fluid model plus some microscopic closures, and after that I applied the filtering approach. So what is the filtering approach? Because I applied another domain. This domain is smaller than coarse grid and bigger than this highly resolved simulation. So for this reason, I want to decrease the time. I want to save time of my simulation. So I applied the filter domain, and also the size of this filter domain exactly the size of the coarse grid inside the real scale. So the filtering is like like something like averaging. So I want to get average on this highly resolved simulation for the all result. So I can easily extract the useful information with this domain, and this domain exactly the size of the larger scale domain, so I can transfer data between the highly resolved simulation to the large scale simulation. So, and here I used two fluid modeling plus microscopic closures, and so after the filtering I have the filtered two fluid models. So here you can see the filtered two fluid equations about the mass conservation equation and about the momentum conservation equation, and this equation as comparison to the normal mass conservation equation and momentum conservation equation, we have some other unknowns variable here, as you can see here. So also for these unknown variables, I need to have some closures. That here you can see the closures like filtered drag force, like drag coefficient correction, and other parameters is related to these unknown variables. So easily I can calculate these unknown variables in the filtered mass conservation equation. Until this slide, this is the method for doing the computational fluid dynamics or safety for the fluidization. But the important thing is that we want to do some improvement about the CFD because we want to increase the accuracy. So for this reason, in these three options, the first and two others is related to two different projects, and all of them, here I try to mention about them. So the first one, the account of the topology related macro scale flow condition. And what's the meaning of this parameter? For example, here, if I want to come back, this is, as I mentioned, that this is my domain. In my simulation, I use like periodic boundary conditions, and this is my domain. And if I want to calculate inside this finest grid size, in our simulation, usually the effect of the parameter in the main domain are usually disregarded. For example, if I want to calculate something inside the grid, the small grid size, the parameter for the main domain are usually disregarded. So this is maybe decrease the accuracy of the simulation. So for this reason, we want to investigate the effect of the some parameter related to the macro. Macro, all parameters are related to the coarse grid size. And after that, I want to introduce the third independent variable as a marker in subgrid closure correlation. And other one, I want to introduce the interparticle friction. About all parameters, I will explain by details in the next slide. And now I'm going to start the introduction of the markers. So what's the meaning of the markers? This is, as you remember, this is my domain, and this is a snapshot of the simulation, performed simulation, and related to the solid volume fraction, means this red part or something, the amount of the solid percent inside the domain you can see. So this is my domain, and this is my filter domain. So if I want to get the filtering at any given time, even at the same time, at different location, the results are not equivalent, because as you can see here, different points are related to the different solid volume fraction. So we can't easily collect all results together. So we need to group the data inside the special table. This table is called bin. And if you want to group the data, you need to have some parameters. For example, you need to group the data inside based off the filtered solid volume fraction. For example, and this range, this range, this range. So you can put the data here. At the end, you can get the statistical averaging at each bins to extract the final result. So in the 2018, the XC started this method by the first marker, the one marker, the filtered solid volume fraction. And after that, in the 2013, Milioli, this is done in the University of Sao Paulo, improved this table to the two markers. And now all researchers use these two markers, or maybe, for example, we can change one of them. So now in my research work, we try to investigate the another markers. So we want to see that, can we improve this table from the 2 markers to 3 markers or not? This is important. Or, for example, maybe in the future, somebody come and say that, okay, we can remove these 2 and we can put another one. So this is just one research. So the main goal of this research to improve the accuracy of the simulation. So this is the bin and this is the marker. So as you remember here, this is the option 2 about the markers, and about the last options about the friction. So, and what's the meaning of the friction? Because as I mentioned before, for my simulation, I applied microscopic two-fluid modeling. So microscopic two-fluid modeling, we have 2 different phases like gas and solid, and both phases treated as interpenetrating continuum phases. So we can solve both phases. So for this main equation, for example, the mass conservation equation or the momentum equation, we need to apply some closures. And these closures, for the solid phase stresses, we apply kinetic theory granular flow. And this kinetic theory granular flow has a very good agreement with the experimental work when we have dilute regimes and also like homogeneous flow. Where something like the inelastic or kinetic collisional effect are dominant. But even in the dilute regimes, for some point, maybe is near to the maximum packing, means that in some point due to the bunch of the particles, and means that the particle is so near together, so maybe friction between the particles is very important. So for this reason, we used two-fluid model with the microscopic kinetic theory of the Bergian-Vescovi, because Bergian-Vescovi tried to modify the kinetic theory of granular flow. Well, actually, in my last slide, as you see that the equations, you couldn't see any effect of the friction. But here, in this modification, we add with this CF, means the friction coefficient, and we try to change all equation based off the friction. So in the last, for example, in the traditional kinetic theory granular flow, if the friction changed, to the equation not change. But here, if the friction change, automatically the equation change. So for my simulation, we use MFIX. This is the open source code written by Fortran. So we implemented all new equation inside the MFIX, and after that we try to know that our code, our equation is work well or not. So for this reason, this is the parameter for the experimental work, and we got this experimental work in 2012, and we run the simulation for the bin discharge. And why we selected bin discharge? Because in the bin discharge, the friction is dominant. So for this reason, we run the simulation with exactly parameter of the experimental work, and we want to know that our code work well or not. So here you can see the solid discharge for like different friction coefficient 0.3, 0.1, 0, and also we didn't apply this new modification. Well, at the first we have a very fast solid discharge, and after that we can reach the plateau regime. But when we didn't apply this modification, you can see completely the weird behavior. And also the experimental work has a value around of the 165, so is more or less near to my simulation, 0.3, as you can see here. So for this reason, at the first we understood that our code is okay, it's true, work well. Undoubtedly we need to improve it for the future, but now it's work well, and also we selected 0.3 our friction coefficient. So, and now with this simulation, with this bin discharge, we want to select the friction coefficient for my simulation fluidization, and I want to show that my simulation is true. So after that, I come in the fluidization, and this is my domain, like periodic boundary conditions. I selected 16 by 16 centimeters, and I applied, this is the subgrid, and these numbers I selected based on my computational source, 128 at each direction. So these values for the properties of the gas or solid for the fluidization I selected, and also for the random simulation, I selected domain average solid volume fraction. In this domain average solid volume fraction related to the macro, means related to this very large domain. So, and this domain changed from the 35% to the 50%. And also for the Reynolds number, I selected from 1 until the 24 because just I want to cover all regimes. For example, from the fixed until the maybe pneumatic regimes. So for this reason, I selected different range of the Reynolds number. So different Reynolds number related to different gas velocity, and also here I selected the domain average solid volume fraction because I'm concerned about the dense regime. So for this reason, I selected 35, 45 until 50. So here, here you can see the simulation animation for the dilute regimes. The red part is related to the gas and blue is a solid. And here you can see that 5%, 15%, 25%. So with increase of the gas velocity, from left-hand side to right-hand side, we have heavier and denser, like cluster or streamers. This is like clusters or streamers inside the gas. And after that, here you can see the animation, the simulation for the 35, 45, and 50. Well, actually, you can see that it's really difficult to see the red part like gas, because here at each over the cross area, we have huge number of the particles. So, well, actually, it's really difficult to see the red part or gas. But here you can see for the 35 solid volume fraction. And this is related to the dense, and here you can see with passing the time, maybe you can see a small part of the gas, but for the 50 is really difficult. So after that, here you can see the counterplot of the solid volume fraction. This one recently published, and this one just we submitted for, this is both for my result. And here you can see that from 5% until 25% domain solid volume fraction, we have more heavier, sorry, can you hear me?
Yes, Reza, you can continue.
Okay.
It's okay.
So here, from the left-hand side to the right-hand side, with the increased domain average solid volume fraction, 5, 15, 25, we have heavier and denser cluster. And also from the top to bottom, with increase of the gas-Reynolds ratio from the 1 until 24, we have like uniform distribution. You can see that, for example, here the flow more uniform, that here means that more homogeneous. And also for the dense regimes from the 35 until the 50, again you can see the more heavier clusters, and also from the top to bottom with increase of the gas-Reynolds ratio, we have more uniform distribution, means that more homogeneous. So based on these contour plots, I want to show some of my result and for different case. So this all result, as you can see here, the all result is for my result, and for example we submitted all of them recently submitted as a paper, and we are waiting for the answer of them, and some of them published also. Okay, so here you can see the effect of the drag correction coefficient as a function of the filtered solid volume fraction. Is function of the filtered solid volume fraction for the unique domain average solid volume fraction 35%, and for the dimensionless filter size 2 by 2, because 4 point is dimensionless. So here unfortunately I couldn't bring all the results, so just I want to show some of my results. So here is a domain solid volume fraction, and here you can see the different filtered axial slip velocity, and this change from the low to high. And as you can see here, for the less than 0.85, and also for the higher value of the filtered solid volume fraction, you can see the effect. Well, actually you can see here different symbols related to different Reynolds numbers here. So higher Reynolds number here, you can see higher Reynolds number related to the lower drag coefficient correction. As you remember in the last slide, I told with the increase here, for example, with the increase of the Reynolds number, the flow will be more uniform. So if the flow will be more homogeneous or distribution more uniform, the drag means interaction between two faces decrease. So, and also here you can see that again in the picture B, for the unique gas Reynolds ratio 8.5, but here for different, as you can see here 1, 8, 16, 24, but this one I selected 1, but for different solid volume fraction. And as you can see here, the behavior of the graphs here and here is the same. So we can conclude and decide that 2 macro scale means domain solid volume fraction, and also the gas Reynolds domain gas Reynolds numbers ratio has the effect on this parameter, so should take into account. And after that, this is just as 2 markers. The important things that, as you remember, before the last slide I spoke about the markers, and here I have just 2 markers, first marker and the second marker. And the next slide, I want to investigate the effect as a third marker, 3 markers. First marker here, the second marker about the slip velocity, and the last one about the like filtered kinetic energy solid velocity fluctuation. Here you can see. Well, because I have 3 markers, so if I want to investigate all 3 markers, really I have a lot of results. So for this reason, I try to investigate the probability density functions. And due to the probability density functions, I try to know the high occurrences of the markers. Means that, for example, here, for the unique filtered solid volume fraction, means that for the 1 marker here, and for the dimensionless filter size, for different Reynolds number, I calculated the filtered axial slip velocity, because I want to know that the amount with the high occurrence of this marker. So as you can see here, the more of them is related to the 0.28. And with this 0.28, I will come in the next step. And here you can see the first marker 0.45, the second marker selected from here 0.28, and now for different Reynolds number I calculated and understood that, okay, so for the high occurrence for this marker is 0.27. So now I can show and I can investigate, or I can calculate my all result for just these 2 values. Because if I want to calculate the all result for the all value, so in this case, many results I have. So for this reason, now I try to show the result just for these 2 values, but just for these 2 values with the high occurrence of the markers. So if I want to explain about the more results, here you can see the effect of the drag coefficient correction H as a function of the filtered solid volume fraction based on the 3 markers. Well, actually, here you can see the high occurrence, as you remember, 0.28. And here you can see for the different filtered kinetic energy solid fluctuation. And as you can see here, for the higher value of the kinetic higher value, and also here Reynolds number, for the higher value here, I have a lower value of the drag coefficient correction. As you remember, I told before, I explained, with increase of the gas Reynolds number, the distribution will be more uniform and the flow will be more homogeneous. So the drag automatically decrease. So for this reason, for the high value of the, here you can see the cycle here, for the high value of the Reynolds number, the drag decrease because the distribution will be more uniform. So after that, now I want to calculate the effect of these markers on the filtered stresses like pressure, like dynamic, like viscosity. And here you can see that for the higher value, for the higher value of the kinetic solid here, kinetic energy here, for the higher value, and also here for the lower value of the Reynolds number, I have higher value of the filtered stress parameters like filtered pressure or filtered viscosity. Here you can see that for the higher value of the kinetic energy and for the lower value of the Reynolds number, for the lower values of the Reynolds number, I have the higher value of the filtered parameters. So filtered parameters like filtered stress is pressure here, P, and for the dynamic viscosity. So why? Because both of these filtered parameters in their equations directly related to the filtered granular temperature. So if the temperature increase, automatically we know that the pressure increase. So as you can see here, has the same behavior, like for the higher value of the kinetic energy here, I have higher value of the granular temperature, And also here, for the lower value of the Reynolds number, I have the higher value of the granular temperature. So for this reason, automatically, because this granular temperature in this equation, so increase, so automatically the pressure or the dynamic viscosity increase. And after that, I want to calculate the effect of the residual stresses, and this parameter related to the pressure here and dynamic viscosity here. So as you can see here, for the higher value of the kinetic energy, higher value of the pressure, and also the same behavior for the dynamic viscosity we have, but there is one difference between the residual stresses and also here filtered parameters. But the reason that in the residual parameter for the Reynolds number I couldn't see any effect. So the Reynolds number doesn't have any effect on the residual parameter, just the kinetic, filtered kinetic energy solid velocity fluctuation, and also I can see this behavior in the dynamic viscosity. And if I want to explain the reason, because in their equation, I show you the equations in my last slides, before slides. So the residual parameter is a function of the shear stress and also scalar shear rate. So here, the shear stress, you can see that for the higher value of the shear stress, so the shear stress increase the pressure or the dynamic viscosity increase. So, and also for about the Reynolds number, you can't see any effect. So this is here we don't have any effect because the pressure or dynamic viscosity as a residual stresses or the function of the shear stress. So we can see any effect also on them. And also again, the residual stresses or parameter are shear rate, and also here you can see that for the higher value of the kinetic energy, we have higher values, so automatically the parameter of the residual stresses automatically increase. Well, actually, if I want to just speak about the summary, about the large-scale two-fluid simulation of the gas-solid fluidized flow requires subgrid closure formulation, because as you remember, because with very coarse numerical grids, we can calculate the effect of the all clusters or streamers. So we need to apply subgrids. And highly resource simulation, because after application of the subgrid models, we can reach the finest grid size as a highly resource simulation. And we applied in this highly resource simulation in the microscopic two-fluid modeling. And also a range of the macro scale conditions and also three independent variables. As you remember, we investigated the effect of the three markers and we saw very good effect about the three markers. So maybe we need to increase our correlation approach were enforced. So another one, accounting for the macro scale condition. Macro scale condition, as I mentioned before, the macro is related to the very coarse numerical grids, and for three independent variables considerably added to the accuracy. So with this way, we want to increase the accuracy of the computational flow dynamics. But well, actually, unfortunately, about the friction, about the filtered parameters, we couldn't see any effect. Well, I can say that the friction doesn't have any effect. Well, because the kinetic theory granular flow in the dense regimes doesn't have any good agreements with experimental work. So well, I can say that the friction doesn't have any effect. We know that, we are maybe sure that, so the friction has effect. So maybe in our code, in our simulations, we need to do some modification, and also we are doing this, and we are trying to improve our code. So well, finally, I would like to say that really thank you for giving me this opportunity, and And again, sorry if I couldn't explain very well, because in this research line we have a lot of details, and this work is I did more than 5 or 6 years, so I'm so sorry if I couldn't explain by details very well. So if I have any questions, it's my pleasure to answer. Thank you very much for your time.
Okay, thank you, Dr. Reza, once again for your nice presentation. And I would like to invite our students and professors to present their corrections. Então, eu agradeci o Dr. Reza. Se alguém tem perguntas, comentários, tem curiosidades, podem abrir o microfone. Você tem palavras em português, a gente, professores aqui da UASC, podemos traduzir sem problema. Se vocês quiserem falar em inglês também, fica à vontade.
Só um comentário, Reza, para você. Tá muito ruim o seu som, não entendi muito bem o que você falou. Não sei se é só comigo, mas... Ok, so Reza Amini, I remember you. We saw you.
Thank you very much. Yes, I thank you very much.
Flesh and blood, almost 2 years ago, I remember.
Yeah,
and so it's very, very good to see you again.
Thank you very much.
And, well, it's very, this kind of research is very complex. You have a lot of effects. I wanted to know what kind of, when do you confront your results with real systems? How do you experiment?
Yes.
Macroscopic physical, you know?
Yes. It's a really thank you. It's a really good question, and well, we are very, very, very far from the real scale, and all the researchers in the world try to improve the accuracy, and because I can say that when we can validate the result of the simulation, because we are very far about the real scales, and now we are in the research line, but about the experimental work or validation is really difficult. But about some cases, like for example about the bin discharge or other parameters, maybe we can do some experimental work. But about this research line, yeah, we are very far from the real scales, and I don't know about this question. Really, I can't answer. So when we can validate, so it's really difficult. So.
Okay, but from the experimental point of view, from the industry and things like that, they have some problems they want you to solve, or somebody is doing that, or what kind of...
Yes. For example,
and what can you measure?
For example, in the fluidized, because my research line about the gas or solid, or fluid, like liquid or solid, because for example, you imagine that, for example, in the pipe system, for example, about the slurry, you want to transfer some materials. Maybe the pressure is really important. You want to investigate or calculate the pressure. So, well, actually, this is maybe one problem, because nowadays in the industry, if you want to transfer like mud, like a slurry, from one point to the 1,000 kilometers another point, so you need to pump. You need to put some pump, for example, to put enough pressure to send this material. So, well, actually, you need to calculate the pressure, or also, for example, due to the drag or due to the friction, we need to calculate a lot of forces, a lot of temperature. So yes, this is completely industrial works, and because yes, we can do a lot of experimental things about this research line. So maybe it has a good cooperation with the industry if it's possible. Yes.
Okay, thank you very much, Reza.
Thank you very much for your good comments.
Sim, Adriano, pode começar.
Oi, Reza, você me escuta bem?
Thank you very much. Thank you very much.
Hi, Reza. Congratulations for your presentation. I'm very happy.
Thank you.
Yeah, very happy because when I see mechanical engineering presenting here in our colloquium, I feel happiness.
Thank you.
Because I'm also mechanical engineering, you know, right?
Yes, I'm happy to see you. Thank you very much. Yes. So
yeah, I have some colleagues as well in São Carlos that have done the doctor course with you, but we can speak later about this one.
Yes, for sure. Yes,
I wrote down a couple of questions here.
Yes, this is my pleasure to answer. Yes, thank you.
Just to respect the time, I'm gonna try to focus in the most important questions from my side, especially the curiosities, right? So first one, the software. What was the software you used for this specific student here from CFD?
Okay, so we use the MFIX.
Okay.
MFIX exactly, they're exactly like OpenFOAM, but it's written by the Fortran and it's a free open source code. And this code is applied by the Energy Department of the US. And after that, I can send the link of this application. It's completely free and has a good, it's very easy. If not means easy, not is like, has a lot of instruction, has a lot of like YouTube movie or something you can start. It's very good to start. It's written by the Fortran. And this application, yes, you can go inside and you can implement your equation at each point, and after that run the simulation. Exactly like OpenFOAM, like this.
Okay,
but
nice to know. But in this software, is it possible to get the mesh? You do the mesh outside, and then you input the mesh into this software, or separate?
Yes. For example, for this case, for my case, I didn't import. Because I didn't import, but before I worked with this application completely by the like Ubuntu, but now in the new generation of the application, exactly like if you open this application, you can say, wow, this is like a commercial software. But completely from the 2018 until after 2018, the application completely changed. So now you can do everything. You can generate your like a geometry. You can go inside like a machine. Yes, but after 2018 version and the new version, the face like a ParaView as you work in like I'm sure that you work with the ParaView exactly like something like this. So it's easily you can generate your geometry. You can apply your mesh. So yes, you can do it.
Okay. And what is the mathematical technique that you used here? The finite volume?
Finite volume method. Finite volume method as the Eulerian method. So because we have two different phases, and these two frames as the Eulerian has the application and interaction together. Yes, exactly.
Yeah. All right. So have you had the chance already to compare the results with another technique like GTT or other techniques available for the same area, or not yet?
Yes, it's very, very, very good questions. And for this comparison, well, actually, because nowadays, even I am working in Japan, in the industrial, I am working just with the two fluids modeling as Eulerian. And so if I'm really interested in one person can write this development method or something, we had a good cooperation, because until now I didn't do, because I need this is maybe start out a very good cooperation with you or something. I'm really happy to do this work.
All right. So congratulations again for the presentation.
Thank you very much.
This is not a simple subject. I would say that this is a very tough subject because this involves multi-phase analysis, turbulence, everything right together.
Thank you.
You are a hero.
Thank you very much. Thank you, and it's my pleasure to if we can have a cooperation together or write any research project or proposal. Really, I appreciate it. It's a pleasure.
Absolutely.
Thank you very much.
Thank you very much as well.
Thank you for your questions. Thank you.
Tá certo. Obrigado, Adriano. Sebastião, pode perguntar.
I have a question for Professor Reza Amini.
Thank you very much. Yes, hi.
And Professor Reza, is it possible to use artificial intelligence in your work?
Yes. For example, recently we started like maybe the technique of the machine learning or something to capture the like for example capture the clusters or streamers. Yes, recently our group started this work. Yes, for sure we can do it, and it's really great to if somebody can help us. It's really for our pleasure. Yes, we started this work.
Thank you, Professor.
Thank you.
Mais perguntas? Então, beleza. Chegamos ao fim, né? Eu gostaria de agradecer de novo, Dr. Reza. I would like to thank you again, Reza, for the participation and your nice presentation. And I would like to see you here in Brazil again one day.
For sure. I like this.
Just for the more information, 2 days ago was the birthday of Dr. Reza. And
Thank you very much.
Here we are going to applause.
Thank you. Yes, thank you very much.
Todo mundo pode abrir o microfone, né? Todo mundo abrir o microfone para né? Para ele.
Thank you very much.
Reza, I have a better idea. Other than inviting Reza to come out of Brazil, we would visit him in Japan.
For sure. This is my pleasure. And also, because another thing is that exactly in every Wednesday in our center, we have like something like this presentation. And really, I want to invite all presenters to present, because here just by Zoom, and it's very easy. So if you are ready or something, I can write and send the letter for you, and so you can do exactly the same presentation in our center, because every Wednesday we have this presentation. Tomorrow in my center we have something like this. So yes, exactly.
Very good.
Thank you very much. Really, thank you. It's my pleasure.
Great. Thank you again. Muito obrigado, pessoal, pela sua presença. Nós vamos continuar nossos colóquios, né? Na semana que vem, vamos ter outro colóquio do professor Marcos, da Universidade de São Paulo. Por hoje, vamos finalizar, né? Até semana que vem. Tchau, pessoal.
Thank you very much for your time. Thank you. Bye. Thank you.
Bye. Bye.
Thank you.